Today we're going to start our lesson on nomenclature. And nomenclature is just a fancy word for naming compounds. The first type we're going to look at is called binary ionic compounds. All binary ionic compounds are composed of two parts. And we've already learned these parts. They're called the cation and the anion. Remember, our cations are positive and our anions are negative. One thing that's really important to remember that in all naming of compounds, the cation is always named first. For type 1 binary ionic compounds, we're going to look at compounds that are formed between metals and nonmetals. It's important for us to know where these are on the periodic table. If we look, we have our metalloid line, and we know that everything to the left is a metal, and everything to the right is a nonmetal. This is really important for all of nomenclature because we have specific rules depending on whether we're naming metals with nonmetals or nonmetals and nonmetals together. In type 1 compounds, the metal only forms one type of cation. So these are our groups that we've looked at, our group 1, our group 2, group 3, etc. And in type 2 compounds, the metal can form two or more cations and have different charges. These are the ones we call our multivalent ions that we looked at the beginning of the year. So we're looking at things like lead and manganese and iron that have multiple ions. The cation is always named first. I said that earlier, but that is really important. And this is for type 1. The cation takes its name from the name of the element. The anion is named by taking the first part of the element name, the root, and adding IDE. So the best way to look at this is to look at examples and to solve some examples. So we're going to name these following compounds. If we look at this, we have sodium and chlorine. To name this, we're going to take the root name of the cation and call it sodium, and we're going to take chlorine and change it to chloride. For our next one, and for right now, just this slide, we're going to ignore those numbers, the subscripts. We're going to learn where those come into play in the next slide. So then we have, we just take the root name, we have aluminum, and we have sulfur. So we're going to call this aluminum sulfide. And then for our third example, we have calcium and bromine, and we're going to call that calcium bromide. And so now if we're going to write formulas for binary ionic compounds, all compounds must have a neutral charge overall. And therefore, we must adjust the number of ions in order to achieve this. So we're looking to make sure that our positives and negatives are equal. It's easy if the ions have the same charge. Okay, so if we have something like sodium fluoride, let's write the ions. Sodium is a group 1 and fluorine is a group 7, and so we know that sodium is +1 and fluorine is -1. Our charge is already neutral, so all we have to do is put the formula together as NaF. For barium sulfide, barium is a group 2 and it's +2. Sulfur is a group 6 and it's -2, and we put that together to get BAS. The charges cancel each other out. And the same is true if we use a group 3, like aluminum. Aluminum is going to be +3, and then nitrogen is going to be -3, and we put those together, the charges are equal, aluminum nitride. What happens when the charges aren't equal? Something like lithium oxide. So we, again, have to write our formula. We have to write Li is +1, because it's in group 1. Oxygen's in group 6, so we have a -2. And we need to balance it off. You often see people do what's called the crisscross method, but only when the charges are not equal. And so in that case, we take just the number, not the charge, and we cross it and bring it down. And by crossing it and bringing it down, we end up with a formula of Li2O. it is okay to write Li2O1. It's not wrong. However, it's not convention. It's not what you'll see anywhere else. And so I'm not going to model that. Although if that helps you when you're beginning to learn, that's okay to do. You'll eventually learn just to drop it because you'll understand formulas. Let's look at another one. Magnesium phosphide. Magnesium is our group 2, so it's +2. Phosphide is a group 5, and so it's a -3. Again, we're going to take just the numbers, not the charges, and crisscross them down. And by doing so, we end up with Mg3P2. We never cross the charges. It's never Mg-3P+2, ever. And for our third example, we have calcium chloride. Calcium is a group 2, so it's +2. Chlorine is a group 7, so it's -1. And so we have calcium +2, Cl -1. Again, we're going to crisscross. I'll draw the crisscross for the 1, but I don't need to write it. And it ends up as CaCl2. It could be Ca1Cl2. Type 2 involves those multivalent ions. So here's the examples of these ones that we've learned, and this chart is also in your textbook. So we have the 2 iron compounds, Fe+3 and Fe+2. We have copper, which is +1 and +2. We have cobalt, which is +3 and +2. We have tin, which is +4 and +2. We have lead, which is +4 and +2. And we have mercury, which is our special one, which is Hg+2 for mercury 2 and Hg2+2 for mercury 1. These are ones that you're going to want to know. So if you don't remember them, please get your flashcards out and start studying. And it's going to show us again. Okay. Formula writing works exactly the same, except we have to specify that charge on the multivalent ion. And we're going to do that by using Roman numerals. So if we have iron 3 chloride, and we already know these Roman numerals, we know that that iron has a +3 charge. And chlorine has a -1 charge. And in fact, some people find these easier because the charge is given to them for their cation. Again, the rules are exactly the same. We crisscross just the number, not the charge, so that we have FeCl3. We have copper 1 sulfide. This is telling us that copper has a +1 charge. Sulfide we know is -2. So we have Cu+1, S-2. Again, cross and cross, and we'll end up with Cu2S. And finally, we're looking at mercury 1 oxide. Mercury 1 is one of our special ones that we have to remember. So that's Hg2+2 and O-2. And if we look at them, this is an interesting one because initially you think you want to crisscross, but we always have to check first if our charges are equal. And remember, if our charges are equal, we just put the formula together. So please don't forget to notice if your charges are the same, you're just going to put it together to form Hg2O. And now for naming these compounds, if we look at something like COCl3, we have to work backwards to figure out what the charge is on our multivalent ion. So if we look at this, we sort of have to uncrisscross and know that this must have come up here, and this invisible one we know is up here because we know Cl is -1. So our 2 ions are Co+3 and Cl-1. This is the one part that's a little bit trickier for these multivalent ions because we have to work backwards to figure out the charge. Once we know it's Co+3, we know what Roman numeral to put in, and we can now call it cobalt-3 chloride. Let's look at another example. We have SN3N2. Again, we're going to uncrisscross, and we'll check that by checking it with the nitrogen. Does nitrogen have a charge with 3 in it? Sure it does. It's -3, which means that SN must have the +2. That helps us know what tin is going to be charge-wise. So we'll call it tin 2 nitride. And then finally, if we look at something like PbO2, this one's a little bit tricky, okay? If we look at our ions and we go to uncrisscross, if I go like this and put an invisible one and I crisscross like this, what I'm going to see is that I'm going to end up with Pb plus 2, O minus 1. That should send up a red flag because I know that oxygen is not a -1. So there's a lot of little details with formula writing that we have to pay attention to. We have to pay attention to if our charges are the same. We have to pay attention to things like ions that we know not getting the proper charges. In which case, this can't be the case. This means that PbO must have been -2, and if I have 2 of them, if I have 2 -2s, then I must have a +4 here. That's what I must be looking at, because if I have 2 -2s, so 2 times the -2, that tells me my total oxygen charge must be -4, which means in order to balance that out, my lead charge must be +4. These aren't common all the time. They're certainly not there all the time that this happens like this, but they're definitely there. So you do need to understand these rules. But that leads us to getting the answer of lead 4 oxide. And that's the end of what we're going to do for the first day. Please make sure you have a good grasp of what we're doing because we're going to do a lot of practice problems. So you want to feel pretty comfortable with what is on this PowerPoint. If not, please watch it again. Also, make sure that you know those multivalent ions because you're going to need to be able to recognize them when they're mixed in with other metals. So you want to know which ones those are. And if you haven't started restudying your polyatomic ions, you're going to need to know those too. For tomorrow, we're going to start with nonmetals and nonmetals. So that's where we'll end, and have a good evening.